Okay, let's just cover some of the cases that come up in many problems that you or the listed formula that you have in the tables for moment of inertia are through axes that go through the center of mass. But in your problem, the axis that you're rotating about may not go to the center of mass. So for example, here is a bar. If the axis went through the center of mass, if this was the O and you're rotating about that, then this axis this way or this way is 1/12 ml square, right? You know that it's 1/12 ml square. Okay, suppose you hang a bar like so, and then you put a pin at some distance. Say if this was the center, you put a distance d from the center. Okay, so it's going to, for instance, at some point in time, it's going to be like that. So it might rotate all the way around, or it might just kind of swing around back and forth, but it's rotating about this axis. So the axis is this way now. It's not at the center, and the distance between the center and the axis, if you take this axis and you take this is your original axis, and you take another axis parallel to this, the distance between them will be d. Okay, so what I would you use now? Because you know only I from here, about this axis, but your motion is actually happening around that axis. Well, turns out there's a proof in bootcamp.org or physics bootcamp.org website that requires calculus, and you can show that if you know this and you know the distance between two such axes, then you know the you would know if you know O, then and this is the axis you're looking for, so you can know about A if you know about O. So this is like O at the center. This result is very important result because it allows you to get moment of inertia about any axis once you know about the center of mass. A parallel axis through the center of mass, an axis which is parallel to the axis that you're working with, but happens to go through the center of mass. If you know that, then you can get the result from the this formula, and this is called parallel axis theorem. So let's see. I had a bar, and I want to M was 10 kilogram, and L was 2 meters, but I was from the end. I was there at maybe 0.2 meter, and I put a pin. I wanted to do and I need for motion, for second law of motion, for rotation, I need an I, and so this I through this axis that I'm working with will just be equal to 1/12 times ml square, that's the center, plus here's the center, that's O, so I need to get a distance. This will be much closer, 0.2 meter will close over here, A. So this whole distance, this is 1 meter, so 0.8 meters, that's the D. So m d square. So you might say m times 1 over 12 L square plus D square. And so you can do m is 10 kilogram, 1 over 12 times 2 square plus D square is 0.8 square. So that will be moment of inertia. I don't need to you can complete this, okay? And this will be kilogram meter square units. So point to notice is this formula or similar formulas in the book, this listed table, have to be modified based on where the axis is. So I'll recommend doing this problem, and I'm not going to do it, but I'll say you do it. So here is a disk, but I'm not going to hang at the center. I'm going to hang at a point which is so the pin is coming out there, and maybe this distance is radius over 3. Okay, so this is the axis and this is the center over here. Let's call it over here. I want you to tell me what will be the moment of inertia about this axis. You can work that out. It's a good example to work with, and I'll see you next video.